everybody. Um, I want to share with you my whiteboard for starting my lecture. And I want to go back to our last model. We are currently studying the panel flutter model, and we started by partial differential equation, and just to have a very fast review of what we presented, I want to show you the previous situation, the past lecture, and in particular we have the following model. We have this initial model. It's just a recap. We started by this equation here, by this physics. We have an external compressible flow, and we have essentially a beam loaded with a buckling load on a bed spring, and we have an initial condition like this and boundary condition. We adopt this eigenfunction method consisting of a general technique allowing to transform a partial differential equation into an ordinary differential equation. And firstly, in general, if we have a time-space equation like that to be imposed to be equal to 0, like our original partial differential equation, we can express both the equation and the unknown in a series of space function, refer to a space function. This space function have the rule of base vector in an infinite dimensional space, and therefore we have an infinite element of base function. So these functions are requested to be independent, essentially. But if they are orthogonal beside independent, it's better, of course. We are lucky. And we proposed a way for producing a set of independent but orthogonal eigenfunction. And the way for producing this eigenfunction is to focus the attention on a specific part of the problem, on the structure, the part involving the conservative elastic force. And we introduce for this scope the eigenfunction, like here. The eigenfunction phi are such that to satisfy this equation. This is the definition. If you are able to solve this equation only in space, this is a space-only equation, this equation will give to you a set of scalar quantity like lambda and function. The scalar quantity has the capability to be positive, always real and positive. The function orthogonal. And so we can find a set of orthogonal functions by studying the structural part of the problem. So going ahead, we have, after determining this eigenfunction for our conservative problem associated with the panel flutter. So in the panel flutter equation, we have a part of the problem which is conservative, another part which is not. So taking into account the conservative part, we can use this conservative part for generating the eigenfunction and the eigenvalue. And that's here the eigenvalues and the eigenfunction for the panel flutter. Okay? Once we have determined these quantities, we can go ahead to solve our original PDE equation. First, assuming for the unknown an exact solution like this, we are authorized to expressed for each time, the displacement for each time as an expansion of this orthogonal function phi, with coefficients which are varied, which a set of infinite coefficient Wn, which variate for any time. So we have infinite time function. Okay? Note that I am not assuming a special hypothesis like separated variable. No. The concept of separated variable is a natural consequence of this point. It's not a constraint, it's not an approximation. It's exact. This expression is exact. If you have a set of orthogonal functions and this function are able to span all the space of the function in that interval, this expression is valid and this series converge in any time exactly to the solution. Okay? So no approximation up to now, and we are assuming point A, this for the solution, and then point B, project the original equation onto each phi n. So take this projection. Each of these projections will give to you the new set of ordinary differential equations. Okay? And we did this phase. We project the original equation. This is the projection here. And we obtain, at the end of the lesson, after this projection phase, we obtain this red equation, which are independent infinite equation, isolated and uncoupled equation as concerning the structural part. Indeed, for this generic mth equation, we have w dot m, double dot w plus omega square w plus, and this here, this part here is not uncoupled because here this summation in n keeps to survive. And therefore, we have obtained a set of ordinary differential equations which are uncoupled as concerning inertia and elasticity, but are coupled in as concerning the aerodynamic aspect here. Okay, and this new set of coefficients A and M can be developed as a skew-symmetric matrix, as we demonstrated here. Okay. In fact, the element A and M is equal to minus A M N. So this set of coefficients coupling our equation is a coefficient as element of a skew-symmetric matrix or anti-symmetric matrix. So at the end of the story, our original PD problem is here transformed to a set of infinite equations. Each of these equations is essentially, these equations are essentially the projection of our original PD equation here, this equation, onto the shape function. Note, I have said projection, but these functions are orthogonal, so the concept of projection is identified with the concept of component. So you can say component of this combination, vectorial combination, or projection, which is the same. The concepts are identical because the functions are orthogonal. We have an orthogonal basis, and therefore component and projection are the same concept. Okay? After this, up to now, the procedure is exact. No approximation. No approximation on transforming a partial differential equation to an infinite number of ordinary differential equations. The approximation arises only when you truncate and you decided to use only a limited set of these equations. Consider only the first 1, 2, 3, 4, 5 equations. Okay? an engineering question. Does this truncation make sense? Can you do this? Are you authorized to truncate? The question is, this depends on the problem you are considering. If you are available to do an approximation, if you are available to represent only process in a limited bandwidth, frequency bandwidth, then you can retain only the first 2, 3, and 4 of this equation. Because, as we can see, the poles of this ordinary differential equation system are typically poles on the complex plane, and we are going to study these poles. And if these poles are such that the imaginary part of this pole is limited in a frequency band, if you are interested to study only time input output signal within this band, then this approximation makes sense. Okay? And this is a very, very important point in aeroelasticity. In aeroelasticity, this implies that if you have a complicated aeroelastic phenomenon and you want to study this space-time phenomenon, you can space discretize your phenomenon and describe your fluid structure interaction in a limited bandwidth, selecting only a subset of your equation involving the pole in that bandwidth you are studying on. Okay? Practical case for aircraft. If you have an aircraft, complicated finite element model, complicated, you have an original continuous problem. If you want to choose your discretized space time variable like this W1, W2, W3, you can use as shape function the mode of vibration of the aircraft, structural mode of vibration, only structure, and you can select the first N mode such that to cover your bandwidth of interest. And you can represent your whole aircraft dynamics in that bandwidth, only selecting the mode within that bandwidth. So this is a fundamental concept in aeroelasticity. Okay, after this preliminary, now we can start by this equation here. After selecting only the first two modes. What first two mode means? First two mode means the following, that the following means that we are considering only first two functions phi1 x equal to sine pi x by L and phi2 equal to sine 2 pi x by L. This means that in your problem, a generic motion like this is decomposed like a summation of this, a combination in any time of this plus, let me do this, you are currently combining this generic function like a summation of this plus this. This is phi1, this is phi2, and here you have W1T and W2T as new unknown, and this is W x comma T, and this is equal almost. Okay, so these two, this and this are the new unknowns, like a vector, and this is a vector in the sense of control systems, a state space vector of time composed by W1T, W2T. So this is a state space vector, and in this framework, our ordinary differential equation system is something like this applied to W1, 2, dot, 1, 0, 0, 1. Look, this here, mass contribution, okay? Trivial inertial, trivial mass matrix. Next, we have a stiffness distribution. Please do not forget this stiffness distribution is omega 1 square and omega 2 square applied to the state space vector 1 and 2. And remind that omega 1 is equal to EI by 1 pi by L to the power 4, okay, minus n bar n pi on R to the power 2 plus k. This is the value of omega 1, and the value of omega 2 is identical, but you have a number 2 here instead of number 1. So you have a 2 here, or you have a 2 here instead of 1. Okay, and up to now, up to this level, you have 2 simple harmonic oscillator up to this level. Okay, you have an uncoupled harmonic oscillator with an omega frequency and with unit mass for both the equation. Okay, so look to the red curve up to this light. This means that you have 2 oscillators for the beam, one like this and one like this, independent. If you don't have aerodynamic, if you don't have damping, if you charge this pendulum or charge this oscillator is able to conserve the energy. But if you include the aerodynamic term, like this term, you have a skew symmetrics or antisymmetric matrix here, like 0, lambda, minus lambda, 0. Applied to, again, the same state space vector. So for this kind of physical system, once you spray discretize this physical system, you have 2 stiffness contribution, one standard diagonal or symmetrics, the other one is a skew symmetrics, as given by the aerodynamics. Moreover, at the end, you have also a damping contribution as a final part of our model here. We have a diagonal damper, zeta 1, 0, 0, and zeta 2. Okay, now, at the end of this story, we want to study the stability of the system. Stability. starting by the case of no damping. Just a fast review of the stability. In the case you have, when you consider the first order differential equation theory, you have a standard state space form like this, x dot, everybody know this, plus a forcing term, by including also the initial condition, okay? This is standard. And how can you study this the stability of this linear system? A very easy way is the following. If you, you can consider two paths for having the same result. The first point of view is the old point of view of calculus point of view. For Italian student, Analisi 1. Calculus is Analisi 1. In the calculus point of view, if you search the calculus point of view, if you search the general free response solution, the structure of free response solution in time is an X free response solution in time, which has the following structure: X tilde by e to the power st. This is an elementary solution for your free problem. And if you assume this, necessary, your time problem becomes Si minus A. We are considering free solution, and then free means cancel the forcing term. Okay, so the original problem becomes this is equal to 0. How can you find non-trivial solution kind of general problem? This implies necessarily that for having non-trivial solution, the determinant of Si minus A be equal to 0. So you have an associated eigenproblem. Okay, so you can determine S1, S2, S3, and so on. And for each S1, S2, S3, you can determine the associated eigenvector like this. As for the n eigenvalues, you have the n eigenvector W tilde n. And so you have many, not only one, you have many elementary solutions satisfying your differential problem, and such that to be not trivial. And you have many, and the linear theory guarantees that the general solution is a combination of all of this. And therefore, the general free solution, X free solution, or the free problem in time, is a combination of all your found solution by the eigenvector multiplied by e to the power s and t. Okay? For n spanning from 1 to the dimension of the space. And this is the free solution. The free solution can be built in this way. So, by calculus or by control system theory, we have that the free solution is something like that. And therefore, the criterion for stability for a linear system is that for any initial condition, for any x0, look, I have a point here. I'm very, very sorry, excuse me. The general solution is a combination of the elementary solution like this, and you have to introduce a coefficient combining the solution. So you have your eigenvector, and you have to add here Cn coefficient. Note that the eigenvector in general are the term apart a constant, and so this constant of the eigenvector help you to build this free solution. But note that if you consider this initial condition and this constant, please consider this point I am discussing, you can fix Cn if you know x0. In fact, if you write this, let me write xt equal to Cn w vector n e to the power s and t. Write this for t equal to 0 at the beginning, and so you have x0, the initial condition, is equal to summation of Cn eigenvector n period. So you have a very linear relationship between your initial condition vector, a matrix built by the eigenvector, by column by column. So this well-known eigenvector matrix here applied to the coefficient matrix C. So you have a linear correspondence between the C coefficient and the initial condition. So the C coefficient are the initial condition. Go back to linear criterion of stability. For any initial condition, namely for any Cn, the free response should be limited in the space, in the state space. Okay? For any initial condition, you perturb your system where an initial condition, your system will keep, you should have a limited response. And the only condition to have a limited response implies that the real part of Sn be less equal to B0. And this is the condition for the stability. Of course, you can go in deep, analyzing the case of strictly inequality or large inequality. If you have a double or a single root for S, blah, 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 are a special case. We don't care. The important thing is that, the important thing is the relationship between this exponential coefficient, this S, and the stability. This is the link of the theory. Okay. Now, this is just a recap, a fast recap. But this is the calculus point of view. Okay. You have an equivalent point of view. And what about this equivalence? Which is the equivalence? The equivalence is the Laplace transform domain. Okay? So the second identical and equivalent point of view is the point of view of Laplace transform point of view. Identical, which means that you have this, and take the Laplace transform. And by taking the Laplace transform, you have Si minus A. And note that the eigenvalues x is now the Laplace transform of x. In the previous vision, this was W, what we call W. Okay, but it is identical. And now, in this vision, instead of calling the pole, instead of calling the S as exponential, characteristic exponential, here you have an exponential. Instead of call this as characteristic exponential in the calculus vision, you call this like Laplace variable. Okay, and you call this value as the value of the transfer function, value of S, such that the transfer function HS loss does not exist. In fact, what is the transfer function H? If you consider the input F, note that for considering a transfer function, you have to consider an input. If you consider an input, output, H is the function such that the output is equal to H as applied to the input. And what about H? It's not difficult to find H. In fact, taking the Laplace transform, look, the Laplace transform of the homogeneous problem is giving you an eigenproblem. If you take the Laplace transform of the forced problem with zero initial condition, you have the following. You have IS minus A multiplied by X tilde equal to F tilde, and therefore X tilde is equal to IS minus A minus 1 by F, and therefore this is H. And so, what about the poles in the Laplace transform world? The poles are the value of the transfer function such that the transfer function does not exist. I mean, a singularity point for the transfer function. And how can I find this singularity point? Imposing that the determinant of H has not meaning. Go to infinite. Note that the determinant of H going to infinite means determinant of Si minus A equal to 0, which is equivalent to the eigenproblem in the calculus point of view. Okay, so this is just the same. These 2 points of view are identical for discussing the stability. Okay, so I take this opportunity to give you just a remind of stability concept. The stability is an essential issues in this course, and unfortunately, this stability here is standard, and unfortunately, we will not have a standard stability. because our ordinary differential equation problem is not an ordinary differential. It's not a polynomial. We have not the determinant to Si minus A to be calculated. We don't have a polynomial. We will have something more complicated. Here we have a polynomial for the panel flutter, but this is a lucky case for the piston theory. The piston theory is simple aerodynamic. It's very simple. Okay? So now go back. Laplace transform approach. So we have take the Laplace transform of this equation 1, this equation 1 with no damping of equation 1 with no damping. We have S square plus omega square 1, 0, 0, omega square 2 plus 0 lambda minus lambda 0, and this is applied to W tilde 1, W tilde 2 equal to 0. Now, somebody could say, okay, but I am a bit confused. Our differential equation problem is of second order. You talked about first order problem in standard form. Is something different? No, it's not different, it's identical. This is a very interesting point of structural dynamics. In structural dynamics, you have typically second order equation because you have the acceleration, and so typically you have second order Lagrange equation of motion in general. It's not the ideal world for a control people. Control people want everything in a first order form, you know. Any kind of evolution problem, development problem in physics, for control people is described by a first order differential equation. But this is not a limitation because you can transform any kind of higher order differential equation in a first order one. You have just to increase the number of equations, you know this point. Why we want to keep in the second order form? Answer for control people is just like a chorus for against control people. Because if I keep the second order form, I can see metrics which have physical meaning for me. Thank you. I can see a mass matrix, I can see a stiffness matrix. If I reduce my system, I can reduce a second order system always in first order form. But the state space matrix, which I will calculate by my original mass matrix and stiffness matrix, loss of meaning for me. Okay? This is the motivation. Now, if you take the determinant, you have essentially something like this. Look at this. S square. You have S square plus omega 1 square. You have a lambda here. You have a minus lambda here. You have an S square plus omega 2 square. It's very, very pretty system. 2 by 2 system. Apply to your W1 and W2. Okay, equal to 0. Now we want to determine our S1, 2, probably 3 and 4. We should have 4 roots by taking this determinant. I will convince you about this. And for each pulse, we will determine our W vector n. From n going from 1 to 4. Okay? First stupid problem. What happens with no aerodynamics? And we are talking about no damping case. No damping. Okay? Okay, what happens for lambda equal to 0. Lambda equal to 0 means no dynamic pressure, no piston theory, only structures. For lambda equal to 0, you have S1, excuse me, you have S square plus omega 1 square by S square plus omega 2 square equal to 0. So you have your 4-pole like S12 equal to plus minus J omega 1, and the other 2 pole, 3 and 4, plus minus J omega 2. So your pole are marginal pole, are on the imaginary axis, and you have one this, one this, one this, and one this, plus J omega 1 minus J omega 1 minus J omega 2 minus J omega plus J omega 2. Okay? Two independent harmonic oscillator, a couple of complex conjugated, two couples of complex conjugated poles. Okay? This is the value. Now what happens if you, please, remember the story that you have omega 1, look, I wrote this, omega 1 here is this, and this omega 1 is the frequency of the beam, including the buckling effect. If you push your beam, this frequency are currently decaying because of buckling, because the buckling is perturbs the dynamic frequency and make the structure flexible and flexible and flexible. So flexible to cancel the stiffness. And this N is able to cancel the stiffness of the first mode and the second one. But for the beam, the story of the beam is different from the story of the plate, because this is a beam essentially. And so the only mode which has the risk to be unstable is the first one. And this means that, you know the story, the Euler critical beam has only one critical buckling deformation, this here, this shape here, not the other. And this means that if you consider not the aerodynamic, but N as root locus parameter, if you consider N bar as root locus parameter, if N is equal to this minus N by this plus this, if you consider N like a root locus parameter, so if you want to face the buckling as a stability problem, as correctly is, you discover that this locus, starting by this situation, is characterized by this motion of the poles, like this and like this. So the first couple is closer and closer to the origin, up to converge and shrink to the origin, coalesce to the origin. Okay? And so this is the root locus for buckling. Take this story and put this apart. Now we want to study not the dependence on N, we want to study the dependence on lambda, which is another story. Okay, so apart this discussion, now write the characteristic equation like S square plus omega 1 square Omega 1 and omega 2 are given, are assigned parameter, are the frequency of the two modal independent oscillator of the structure. A square plus omega 2 square. And here we have this lambda, so we have plus omega square equal to 0. Okay? Now I have an interesting question to you. Develop this equation. We have a fourth order equation, a square, we have plus omega 1 square plus omega 2 square, a square, and look, plus omega 1 square, omega 2 square, plus lambda square. Now I have a question to you. Remember, we are studying this problem. Give me just a minute. Do you have time for a minute? Thank you. We are studying this problem. Okay. I want to use this YouTube link here. Do you remember this experiment? I showed you. This experiment is the panel flutter experiment. And the panel flutter experiment is giving to you this kind of experience. Here you have a wind here, and you have this kind of oscillation. Okay, look, this is an unstable oscillation. There is a couple of eigenvalues at the margin of stability going ready to cross the imaginary axis, just ready to cross the imaginary axis. And this is dynamic stability. You can see a frequency. You can see a frequency. Question: is it possible to have a static instability caused by the wind? So it is possible to have just like the buckling, but not caused by the buckling, caused by the wind, the flow. Is it possible to have a static stability with lambda not equal to 0? Question again, is it possible to have a static instability, 0 poles, for a value of lambda? You have the answer to this equation. The answer is written in this characteristic equation. Look, you have a second order equation, fourth order equation, s square, s to the power 4, s square, and this is the non-term undependent by s. Is any physical value for lambda such that you have s equal to 0? The condition for have a steady pole means a 0 pole in the origin. The necessary condition is that this term be 0. Okay, but this term 0 means lambda equal to minus omega 1 square, omega 2 square, right? So this number is negative number. So there is not any physical solution able to giving you a static instability or which means 0 pole for the panel flutter. The panel flutter is only flutter, is not the panel divergence, is panel flutter, period. We can't have, the model is not able to give you steady stability solution, okay? Whereas the buckling is exactly the opposite. In the buckling instability, you may have only static instability. Okay? So I finish here, and tomorrow I'll continue this discussion and complete this discussion with I will complete the exercise with you, and for having a clear idea, a complete idea of this problem. Okay? If you have a question, you have time for a question, I'm here, available.